The event horizon is the defining feature of a black hole, the boundary that separates the inside from the outside, the point of no return. It is not a physical surface, nothing material exists there. It is a boundary in spacetime itself, a geometric feature defined by gravity so intense that escape velocity exceeds the speed of light. Imagine spacetime as a fabric. Normal matter creates gentle dips in this fabric. The sun creates a modest well, Earth a tiny dimple. But a collapsing stellar core creates something far more extreme. As matter compresses toward infinite density, it curves spacetime more and more severely. The dip becomes a funnel, the funnel becomes infinitely deep. At a critical radius, the Schwarzschild radius, named after Karl Schwarzschild, who calculated it in 1916, spacetime curves so steeply that light itself cannot climb back out. This radius depends only on mass. For a stellar mass black hole of 10 solar masses, it's about 30 kilometers. For a supermassive black hole of 1 billion solar masses, it's about 3 billion kilometers, roughly the distance from the Sun to Uranus. The moment the collapsing core shrinks within its Schwarzschild radius, an event horizon forms. Everything inside this boundary is causally disconnected from the outside universe. No signal, no information, no influence of any kind can cross from inside to outside. The event horizon is a one-way membrane in spacetime. From the outside, we see the stellar envelope still collapsing. We see a supernova, the outer layers rebounding and exploding outward. But at the center, hidden from view, a region of spacetime has pinched off from the rest of the universe. The black hole exists, silent and invisible, defined only by its gravitational influence. In the vast darkness of space, there exist regions so extreme, so fundamentally strange, that they challenge everything we think we know about reality. Places where time stops, where space curves infinitely, where the laws of physics as we understand them break down completely. These are black holes, cosmic abysses from which nothing, not even light, can escape. Tonight, we embark on a journey through the complete life cycle of these mysterious objects. From their violent births in the depths of massive stars, through their long existence as the universe's most efficient destroyers and recyclers of matter, to their ultimate fate, a slow evaporation back into the quantum foam from which all things emerge. Black holes are not merely astronomical curiosities. They are fundamental to understanding the universe. They lurk at the centers of galaxies, shaping cosmic evolution. They test the limits of Einstein's general relativity. They connect to the deepest questions in physics, the nature of space and time, the fate of information, the relationship between quantum mechanics and gravity. What happens when you fall into a black hole? Can anything truly escape their grasp? What exists at their centers, hidden behind the event horizon? How do supermassive black holes grow to billions of times the sun's mass? And perhaps most mysteriously, how do black holes die? These questions have fascinated scientists for over a century, since Karl Schwarzschild first solved Einstein's equations and discovered that massive objects could curve spacetime so severely that escape becomes impossible. Close your eyes, breathe deeply, and let us descend together into the abyss to understand these cosmic enigmas from birth to evaporation. Every black hole begins with a star. Not just any star, but a massive one, at least 8 to 10 times the mass of our Sun, though most black hole progenitors are much larger. These stellar giants live fast and die spectacularly, and their deaths give birth to the universe's most extreme objects. A massive star spends its life in a constant battle against gravity. Nuclear fusion in its core generates heat and pressure that push outward, counteracting the star's tendency to collapse under its own weight. For millions of years, this balance holds. The star fuses hydrogen into helium, helium into carbon and oxygen, carbon into heavier elements, building up a layered structure like a cosmic onion. But fusion has limits. Each fusion stage produces less energy than the last and exhausts its fuel faster. Hydrogen fusion might last millions of years. Silicon fusion, the final stage before iron, lasts only days. The star is racing toward an inevitable end. Iron is the finish line. Fusing iron requires energy input rather than releasing it. When an iron core forms at the star's center, fusion stops. Suddenly, there is nothing to support the core against gravity. The outward pressure vanishes. The core, containing more than the sun's entire mass compressed into a sphere the size of Earth, has only one possible fate: collapses. And when it collapses, it does so catastrophically in less than a second. The core that took millions of years to build implodes faster than a heartbeat. This is not a gentle process. This is the universe demonstrating the overwhelming, irresistible power of gravity when nothing remains to oppose it. The collapse of the stellar core is one of the most violent events in physics. In a fraction of a second, matter falls inward at speeds approaching 1/4 the speed of light. Electrons are crushed into protons, forming neutrons and releasing neutrinos. The temperature soars to hundreds of billions of degrees. The core shrinks rapidly, from Earth-sized to city-sized in less than a second. Density becomes incomprehensible. A teaspoon of this collapsing matter would weigh as much as a mountain. Space itself is being compressed, warped by the intense concentration of mass. For stars between about 8 and 25 solar masses, the collapse halts when the core reaches nuclear density, when neutrons pack so tightly they touch. Neutron degeneracy pressure, a quantum mechanical effect, provides resistance. The collapse stops. The core rebounds, sending a shock wave outward through the infalling stellar envelope. This shock wave tears the star apart in a supernova explosion. What remains is a neutron star, a stellar corpse about 20 kilometers across, composed almost entirely of neutrons, spinning rapidly and possessing intense magnetic fields. Neutron stars are extreme, but they are stable objects governed by known physics. But for more massive stars, those exceeding about 25 solar masses, even neutron degeneracy pressure is insufficient. The core's mass exceeds the Tolman-Oppenheimer-Volkoff limit, roughly 3 solar masses, beyond which no known force can prevent further collapse. The collapse continues. The core shrinks past nuclear density, past any density known to physics. It continues collapsing toward a mathematical point, a singularity. And as it does, something remarkable happens to the spacetime around it. An event horizon forms. A black hole is born. Real black holes are not static and spherical. They rotate because the stars that form them rotate. A rotating black hole is described by a different solution to Einstein's equations, discovered by Roy Kerr in 1963. The Kerr solution is far more complex than Schwarzschild's, but it reveals fascinating features. A rotating black hole drags spacetime around with it. Imagine spacetime as a fluid. The spinning black hole is like a marble rotating in honey, dragging the honey along. This frame-dragging effect means that near a rotating black hole, space itself is rotating. To remain stationary relative to distant stars, you would need to move opposite to the black hole's rotation. Close enough to the black hole, frame dragging becomes so strong that remaining stationary is impossible. You're forced to co-rotate with the black hole. This region is called the Ergosphere, from the Greek word for work, because energy can theoretically be extracted from this region. The ergosphere exists outside the event horizon. You can enter it and escape, unlike the event horizon itself. But while inside, you cannot help but orbit in the direction of the black hole's spin. The faster the black hole rotates, the larger the ergosphere. At the event horizon of a rotating black hole, the geometry is more complex than for a Schwarzschild black hole. There are actually two horizons, an outer event horizon and an inner Cauchy horizon. The mathematics predict strange properties for the region between them, though these regions are likely unstable and may not exist in physical black holes. The maximum rotation rate for a black hole is limited. If rotating too fast, the event horizon would disappear, exposing the singularity, creating a naked singularity. From our perspective, watching from a safe distance, something strange happens to matter falling into a newly formed black hole. As objects approach the event horizon, they appear to slow down. The closer they get, the slower they move. They become redder as their light stretches to longer wavelengths. They dim, fading from view. At the horizon itself, from our perspective, time stops. An infalling object appears frozen, forever approaching but never quite crossing the boundary. This is not an illusion. This is a real feature of spacetime near a black hole, a consequence of gravitational time dilation. Einstein's general relativity tells us that gravity affects time. Clocks run slower in stronger gravitational fields. On Earth, a clock at sea level runs slightly slower than a clock on a mountaintop. Near a black hole, this effect becomes extreme. As you approach the event horizon, time, as measured by a distant observer, slows dramatically. An observer watching you would see your clock ticking slower and slower. At the horizon, from their perspective, your clock stops entirely. They never see you cross. They see you frozen in time, gradually redshifting and dimming until you fade from view. But from your perspective, falling toward the black hole, nothing special happens at the horizon. You don't slow down. You don't stop. You cross the event horizon in finite time according to your own clock. There is no barrier, no wall, no sensation. For a large black hole, you might not even notice crossing. The tidal forces at the horizon of a supermassive black hole are negligible. This divergence between perspectives is one of black hole physics' most puzzling features. Both descriptions are correct in their own reference frames. Once you cross the event horizon, your fate is sealed. All paths through spacetime now lead inward, toward the singularity at the center. Escape is not merely difficult, it is geometrically impossible. The singularity is not a place you can avoid by maneuvering. It is in your future, as inevitable as next Tuesday. Inside the horizon, the roles of space and time become exchanged in a sense. Outside the black hole, you can move freely through space but are dragged inexorably forward through time. Inside, you can move freely through time's direction, though only toward the singularity, while the radial direction toward the center becomes timelike. Moving toward the center is not a choice but an inevitable progression through time. As you fall inward, tidal forces grow. These forces arise because gravity is stronger closer to the mass. Your feet, closer to the center than your head, experience stronger gravitational pull. This difference stretches you. For a stellar mass black hole, these tidal forces become extreme even before you cross the horizon, stretching you into a thin stream of atoms in a process physicists grimly call spaghettification. For a supermassive black hole with its much larger event horizon, tidal forces at the horizon are weak. You could cross safely, but as you continue falling inward, the tidal forces eventually become lethal. No material can withstand the stretching as you approach the singularity. The journey from horizon to singularity is finite and brief. For a stellar mass black hole of 10 solar masses, From crossing the horizon to reaching the singularity takes about 10 microseconds. You have no time to contemplate your fate. For a supermassive black hole, the journey might last minutes or hours, depending on mass, but the end is the same. At the center of every black hole, general relativity predicts a singularity, a point where space-time curvature becomes infinite, where density becomes infinite, where the known laws of physics break down completely. This is not a place but a moment, the end of time for anything that falls in. What is the singularity? Mathematically, it is a point where the equations of general relativity produce infinities. Physical quantities like density and tidal forces become undefined. Space-time itself becomes so severely curved that it ceases to have meaning in the way we normally understand it. But most physicists believe the singularity is not physically real in the form described by general relativity. Instead, it represents a boundary where general relativity fails, where quantum effects must become important. At the extreme densities and small scales near the singularity, we need a theory of quantum gravity, a theory that unites general relativity with quantum mechanics. We don't have such a theory yet. String theory, loop quantum gravity, and other approaches to quantum gravity suggest the singularity might be replaced by a more complex structure. Perhaps a region of quantum foam, perhaps a bounce that connects to another region of spacetime, perhaps something we cannot yet imagine. The singularity is a signpost marking where our understanding ends. For a rotating black hole, and all realistic black holes rotate since they form from rotating stellar cores, the singularity is not a point but a ring. The mathematics predict a ring singularity with peculiar properties, including the theoretical possibility of passing through it into other regions of spacetime or even other universes. These are solutions to Einstein's equations, but likely not physical realities. The singularity remains hidden behind the event horizon, forever invisible to outside observers. After a black hole forms, it quickly settles into a remarkably simple state. All the complexity of the star that created it, its chemical composition, magnetic fields, surface features, internal structure, is lost. The black hole is described by just 3 numbers: mass, angular momentum, spin, and electric charge. This is encapsulated in the No-Hair Theorem, a principle in general relativity stating that black holes have no distinguishing features beyond these 3 quantities. 2 black holes with the same mass, spin, and charge are completely identical, regardless of what formed them. All other information about the original star has been erased. The name No-Hair suggests the black hole is smooth and featureless, like a bald head. It has no hair, no additional details or characteristics. Whether the black hole formed from a star made of hydrogen or iron, whether the star had planets or not, whether it was rotating clockwise or counterclockwise, none of this matters. Only mass, spin, and charge remain. In practice, black holes in nature have essentially zero net electric charge. Charge would attract opposite charges from the surrounding plasma, quickly neutralizing the black hole. So realistic black holes are described by just 2 numbers, mass and spin. The spin is crucial. A rotating black hole drags spacetime around with it in a process called frame dragging. Near the event horizon, this dragging is so severe that nothing can remain stationary. Everything is pulled along in the direction of rotation. This region of dragged spacetime is called the Ergosphere. The black hole's simplicity is striking. From the death of a complex star arises an object of geometric purity, a pure gravitational field described by simple equations. All information beyond mass and spin appears lost forever. The simplest black hole is one that doesn't rotate and has no electric charge. This is described by the Schwarzschild solution to Einstein's field equations, discovered by Karl Schwarzschild in 1916, mere months after Einstein published general relativity. Schwarzschild was serving in the German army during World War I when he made this calculation, solving Einstein's complex equations for the spacetime around a spherically symmetric mass. Tragically, Schwarzschild died of an illness contracted at the front shortly after publishing his solution. He never knew the profound implications his work would have. The Schwarzschild solution reveals that for any mass, there exists a critical radius, the Schwarzschild radius, where the escape velocity equals the speed of light. For the Sun, this radius is about 3 kilometers. For Earth, it's about 9 millimeters. These objects are much larger than their Schwarzschild radii, so no event horizon forms. But if you could compress the Sun to within 3 kilometers radius, or Earth to within 9 millimeters radius, an event horizon would form. The object would become a black hole. The Schwarzschild radius depends only on mass. It's proportional to mass, approximately 3 kilometers per solar mass. The Schwarzschild solution describes spacetime outside the event horizon. Spacetime is curved by the mass, creating gravitational effects. Light bends around the black hole. Orbits are possible at various distances, though the innermost stable orbit is at 3 times the Schwarzschild radius. Inside the event horizon, the Schwarzschild solution predicts inevitable collapse to the central singularity. Time and space exchange roles. The singularity is not a place you can visit and leave. It is a moment in your future that you cannot avoid once you've crossed the horizon. This is the geometrical inevitability of black holes. The black holes we've discussed so far, those formed from collapsing stars, are called stellar mass black holes. They range from about 3 solar masses, the minimum for black hole formation, to perhaps 100 solar masses, depending on the progenitor star's mass and how much material is expelled in the supernova. Our galaxy, the Milky Way, likely contains 100 million stellar mass black holes, according to theoretical estimates. Yet we've confirmed only a few dozen. Most drift silently through space, invisible unless they accrete matter or have a companion star revealing their presence through orbital dynamics. Stellar mass black holes form in the depths of the most massive stars. Stars exceeding about 25 solar masses are candidates, though the exact mass threshold depends on factors like rotation and metallicity. More massive stars produce more massive black holes, up to a limit imposed by instabilities during the star's evolution. There's a gap in the observed black hole mass distribution. We see stellar mass black holes up to about 50 or 60 solar masses from direct observations and gravitational wave detections. We see supermassive black holes starting at hundreds of thousands to millions of solar masses in galaxy centers. But intermediate mass black holes between 100 and 100,000 solar masses are rare and controversial. This gap might be real, reflecting limits on stellar evolution and black hole formation mechanisms. Or it might be an observational bias. Intermediate mass black holes are harder to detect than stellar mass black holes in binaries or supermassive black holes in galaxy centers. Recent gravitational wave detections hint at black holes in the upper stellar mass range, pushing toward the intermediate mass regime, suggesting the gap may partially be filled. A black hole in isolation is invisible, a dark void against the darkness of space, detectable only through its gravitational influence. But when a black hole has nearby matter to consume, it becomes one of the most luminous objects in the universe. The key to this transformation is the accretion disk. When gas, dust, or stellar material falls toward a black hole, it doesn't fall straight in. It has angular momentum, some amount of sideways motion. Conservation of angular momentum means this material cannot fall directly to the event horizon. Instead, it spirals inward, forming a rotating disk of matter around the black hole. This disk is not a solid structure. It's a swirling maelstrom of gas and plasma, with inner regions orbiting faster than outer regions. Material in the disk gradually loses angular momentum through friction and magnetic interactions, allowing it to spiral slowly inward toward the event horizon, while the lost angular momentum transfers outward. The friction generates tremendous heat. As particles rub against each other, as magnetic fields twist and reconnect, gravitational potential energy converts to thermal energy. The inner regions of the accretion disk, moving at a significant fraction of light speed, heat to millions of degrees. At these temperatures, the disk glows brilliantly. The hottest inner regions emit X-rays. Cooler outer regions emit ultraviolet and visible light. The accretion disk of an actively feeding black hole can outshine entire galaxies. A black hole accreting at maximum efficiency converts about 10% of infalling matter's rest mass to radiated energy, far more efficient than nuclear fusion, which converts less than 1%. The disk's appearance depends on viewing angle. Edge-on, we see a thin, bright line. Face-on, we see a glowing disk with a dark shadow in the center, the photon sphere where light orbits the black hole. Some accreting black holes produce another spectacular feature: jets. These are narrow beams of plasma and radiation that shoot outward from near the black hole's poles, perpendicular to the accretion disk, at speeds approaching the speed of light. Jets can extend for millions of light years, far beyond the galaxy hosting the black hole. The exact mechanism producing jets is not fully understood, but it involves the interaction between the black hole's spin, the accretion disk, and magnetic fields. Magnetic field lines threading through the disk become twisted by the disk's differential rotation. These twisted fields can extract rotational energy from the black hole itself through a process called the Blandford-Snejek mechanism. The magnetic fields channel plasma from the disk's inner regions and accelerate it to relativistic speeds along the rotation axis. The result is two opposing jets, one from each pole. The jets are collimated, meaning they stay narrow rather than spreading out, focused by magnetic fields into beams that can remain coherent across intergalactic distances. Particles in jets reach extraordinary energies. When they eventually collide with intergalactic gas or enter intergalactic magnetic fields, they produce radio emission. This is why many black hole jets are detected through radio telescopes. The jets show knots and variations in brightness, indicating instabilities and shocks within the outflowing plasma. Jets have profound effects on their surroundings. They punch through galaxies, heating intergalactic gas, preventing it from cooling and forming stars. In galaxy clusters, black hole jets excavate enormous cavities in the hot intracluster medium, bubbles millions of light years across. This feedback from black holes regulates galaxy growth, connecting black hole physics to the evolution of the largest structures in the universe. Not all accreting black holes produce jets. The presence of strong jets seems to correlate with black hole spin and black holes emit no light of their own. The event horizon is perfectly black. Yet astronomers have identified thousands of black holes throughout the universe. How do we detect objects that are fundamentally invisible? The first method uses binary systems. If a black hole has a companion star, the star orbits the common center of mass. By observing the star's motion, measuring how it wobbles or varies in velocity, we can infer the presence of an unseen massive companion. If that companion's mass exceeds 3 solar masses, the maximum for a neutron star, it must be a black hole. The first stellar mass black hole candidate discovered this way was Cygnus X1, identified in 1964 as an X-ray source and confirmed as likely containing a black hole through orbital studies of its blue supergiant companion star. The The system emits powerful X-rays because matter from the supergiant flows onto an accretion disk around the black hole. X-ray emission is itself a detection method. Black holes accreting matter heat that matter to millions of degrees, producing copious X-rays. X-ray binary systems, a visible star paired with an X-ray source, are prime black hole candidates. By measuring the X-ray variability and orbital parameters, astronomers distinguish black holes from neutron stars. Gravitational microlensing provides another detection method. When a massive object passes between us and a distant star, its gravity bends the star's light, briefly magnifying and brightening it. Isolated black holes drifting through the galaxy occasionally cause such lensing events. By analyzing the light curve, how the brightness changes over time, astronomers can estimate the lensing object's mass and sometimes confirm it's a black hole. More recently, gravitational waves have revolutionized black hole astronomy. When black holes merge, they emit ripples in spacetime detectable by instruments like LIGO and Virgo. On September 14, 2015, humanity detected gravitational waves for the first time. Two black holes, each about 30 solar masses, spiraled together and merged 1.3 billion light-years away. The collision sent ripples through spacetime that reached Earth, stretching and compressing space by less than the width of a proton. Yet our instruments detected this whisper from the cosmic deep. Gravitational waves are predictions of Einstein's general relativity, described in 1916 but thought undetectable due to their weakness. Einstein himself doubted we would ever observe them, but advances in laser interferometry made detection possible. LIGO, the Laser Interferometer Gravitational Wave Observatory, uses laser beams traveling along 4-kilometer arms to measure minute changes in spacetime. When a gravitational wave passes through LIGO, it stretches space in one direction while compressing it perpendicular to that, creating a characteristic pattern. The September 2015 detection showed the unmistakable signature of two black holes merging, a chirp that increased in frequency and amplitude as the black holes spiraled together, culminating in the ring-down as the merged black hole settled into its final state. This detection confirmed black holes exist. No other known objects could produce the observed signal. Since then, dozens of black hole mergers have been detected, revealing a population of black holes across a wide mass range. We've learned that binary black holes are common, that they merge frequently throughout the universe, and that their properties match theoretical predictions remarkably well. Gravitational wave astronomy opens a new window on the universe. Unlike light, gravitational waves pass through matter unimpeded. They carry information from the most violent events, black hole mergers, neutron-star collisions, directly to us. We are beginning to hear the universe's gravitational symphony, conducted by spacetime itself. On April 10, 2019, humanity saw a black hole for the first time. Not indirectly through X-rays or gravitational effects, but directly, an image of the event horizon's shadow against the glowing accretion disk. The black hole at the center of the galaxy M87, 55 million light-years away, appeared as a dark circle surrounded by a bright ring of light. This image required a telescope the size of Earth. The Event Horizon Telescope is not a single instrument but a network of radio telescopes scattered across the globe, from Hawaii to Chile to Antarctica. Operating together using very long baseline interferometry, they function as one Earth-sized radio telescope with unprecedented resolution. The target was M87's central black hole, one of the universe's most massive 6.5 billion solar masses. At that distance, the event horizon's angular size is about 40 microarc seconds, like viewing a donut on the moon from Earth. Only the combined power of multiple telescopes across Earth could resolve such a tiny feature. The image shows exactly what general relativity predicts. The dark circle, the black hole's shadow, is slightly larger than the event horizon due to gravitational lensing. Light from the accretion disk bends around the black hole, creating a photon ring where photons orbit before escaping. The bright crescent on one side results from relativistic beaming. Material orbiting at nearly light speed appears brighter on the side moving toward us. Later, the Event Horizon Telescope imaged Sagittarius A*, the supermassive black hole at our own Milky Way's center. Though much closer, only 26,000 light-years, it's also much smaller, about 4 million solar masses. Its rapid variability made imaging more challenging, but the result confirmed our galaxy's central black hole resembles M87's in fundamental structure. A black hole evaporates through Hawking radiation, but this process is extraordinarily slow for stellar mass and larger black holes. The timescale for complete evaporation depends on the cube of the black hole's mass. Double the mass, and evaporation takes 8 times longer. For a solar mass black hole, the evaporation timescale is about 10 to the 67th power years, far longer than the current age of the universe, which is merely 1.4 times 10 to the 10th power years. The black hole would still be essentially unchanged after countless eons, slowly radiating at a temperature billions of times colder than the cosmic microwave background. For supermassive black holes, the timescale is even more extreme. A billion solar mass black hole would take 10 to the 94th power years to evaporate, a number so vast it defies comprehension. To put this in perspective, this is 10 to the 84th power times longer than the universe's current age. But the evaporation accelerates as the black hole loses mass. When the black hole reaches planetary mass, about the mass of Earth, its temperature rises to a few thousand Kelvin, and evaporation proceeds faster. At asteroid mass, temperature reaches millions of degrees, and the black hole radiates intensely. In the final moments, when the black hole has shrunk to microscopic mass, the process becomes explosive. The temperature soars to billions of degrees. The black hole emits all types of particles, photons, neutrinos, gravitons, everything allowed by physics. In the final second, the black hole releases energy equivalent to millions of nuclear weapons. Then, in a final burst of radiation, the black hole vanishes. What remains is debated, perhaps nothing, perhaps a Planck mass remnant, perhaps something we cannot predict without a complete theory of quantum gravity. At the centers of most large galaxies, including our own, lurk supermassive black holes containing millions to billions of solar masses. These monsters are fundamentally different from stellar mass black holes in scale but not in nature. They are still described by the same mathematics, still defined by event horizons and singularities, still ultimately subject to the same physical laws. The supermassive black hole at the Milky Way center, Sagittarius A*, pronounced A*, contains about 4.2 million solar masses compressed into a region smaller than Mercury's orbit. We've observed stars orbiting this black hole, their elliptical paths revealing the central mass. One star, S2, orbits in just 16 years, reaching speeds of nearly 5% of light speed at closest approach. The black hole in M87, imaged by the Event Horizon Telescope, contains 6.5 billion solar masses. The most massive known black holes exceed 10 billion solar masses, as massive as small galaxies, yet compressed to regions comparable to our solar system's size. How do supermassive black holes form? This remains one of astronomy's major questions. They appear very early in cosmic history. We observed supermassive black holes when the universe was less than 1 billion years old. Growing a billion solar mass black hole in less than 1 billion years is challenging, even assuming continuous accretion at maximum rates. Several formation scenarios have been proposed. Direct collapse of massive gas clouds in the early universe, creating seed black holes of thousands or tens of thousands of solar masses. Runaway mergers of stars in dense clusters, or growth from stellar mass black holes through continuous accretion and mergers. Likely, multiple pathways contribute to building the supermassive black hole population we observe. When supermassive black holes actively accrete matter, they power the universe's most luminous persistent sources, quasars and active galactic nuclei, or AGN. A single quasar can outshine its entire host galaxy, making them visible across billions of light-years. The light comes not from the black hole itself, but from the superheated accretion disk surrounding it. Quasars are most common in the distant, early universe, when galaxies were smaller and gas-rich, providing ample fuel for black hole growth. As we look farther out, and thus farther back in time, we see more quasars. The quasar era peaked when the universe was about 2 to 3 billion years old, during the epoch of maximum cosmic star formation. Not all supermassive black holes are actively accreting. Our Milky Way's central black hole is relatively quiet, accreting at a trickle compared to its maximum capacity. It produces some radio emission and occasional X-ray flares when it captures passing gas clouds, but it's not a quasar. Most supermassive black holes today are similarly dormant, having exhausted their local fuel supply. The relationship between supermassive black holes and their host galaxies is profound and not fully understood. Black hole mass correlates tightly with properties of the galactic bulge, the dense central region of stars. More massive bulges host more massive black holes, following a consistent relationship. This suggests black holes and galaxies co-evolve, influencing each other's growth. AGN feedback, energy, and momentum from accreting black holes regulates star formation in galaxies. Jets and radiation from the central black hole can heat or expel gas, preventing it from cooling and forming stars. This negative feedback may explain why the most massive galaxies stop forming stars, transitioning to quiescent, red and dead systems dominated by old stellar populations. Black holes pose a fundamental challenge to physics through what's known as the information paradox. Quantum mechanics states that information cannot be destroyed. The quantum state of a system determines its future and past completely. But general relativity says anything falling into a black hole is lost forever, trapped behind the event horizon. These principles appear incompatible. When matter falls into a black hole, it carries information, the quantum states of all its particles, determining their properties and configurations. According to classical general relativity, this information crosses the event horizon and eventually reaches the singularity, disappearing from the universe. No measurement outside the black hole can recover this information. The black hole remembers only its total mass, spin, and charge, no other details. This loss of information violates quantum mechanics reversibility. Given the universe's complete quantum state at one time, you should be able to calculate its state at any other time, forward or backward. But if information falls into black holes and vanishes, this reversibility is broken. The universe's quantum state becomes unpredictable. The paradox deepens when we consider Hawking radiation, which we'll explore later. Hawking showed that black holes slowly evaporate, emitting thermal radiation and eventually disappearing completely. If the black hole evaporates entirely, taking the information with it, then information is truly destroyed, violating quantum mechanics. But if the information somehow escapes in the Hawking radiation, we need a mechanism for that escape, which general relativity doesn't provide. This is not merely an academic puzzle. It touches the foundations of physics, suggesting our understanding of quantum mechanics, general relativity, or both is incomplete. Resolving the information paradox likely requires a theory of quantum gravity, a framework uniting these two pillars of modern physics. In 1974, Stephen Hawking made a discovery that revolutionized our understanding of black holes. Using quantum field theory in curved spacetime, he showed that black holes are not perfectly black. They emit radiation, they have temperature, and most remarkably, they slowly evaporate, eventually disappearing completely. Hawking's insight involved quantum mechanics at the event horizon. In quantum field theory, vacuum is not empty. Particle-antiparticle pairs constantly appear and annihilate. Normally, these virtual particles exist only briefly, borrowing energy from the vacuum and returning it before violating energy conservation detectably. But near a black hole's event horizon, something remarkable happens. A particle-antiparticle pair can appear with one particle just inside the horizon and one just outside. The particle inside falls into the black hole, unable to escape. The particle outside can escape to infinity, becoming real rather than virtual. From the outside, this appears as though the black hole emitted a particle. The black hole loses mass equal to the particle's energy, mass energy extracted from the black hole itself. This emission is Hawking radiation, and it gives black holes a temperature inversely proportional to their mass. For stellar mass and supermassive black holes, Hawking temperature is incredibly low, far below the cosmic microwave background temperature. A solar mass black hole has a temperature of only 60 nanokelvins, about 10 million times colder than the microwave background. Such black holes absorb more energy from the universe than they emit through Hawking radiation. They grow rather than shrink. But as a black hole loses mass through Hawking radiation, its temperature increases. Smaller black holes are hotter. This creates a runaway process. The hotter the black hole, the faster it evaporates, the hotter it becomes. Eventually, this leads to complete evaporation. Hawking's discovery revealed a deep connection between black holes, thermodynamics, and quantum mechanics. Black holes are not just gravitational objects, they are thermodynamic systems with temperature, entropy, and all the properties of systems studied in statistical mechanics. The temperature of a black hole is inversely proportional to its mass. This seems counterintuitive at first. In normal objects, more mass usually means more thermal energy and higher temperature. But black holes are different. A more massive black hole has a larger event horizon, which means a lower surface gravity at that horizon, which translates to a lower Hawking temperature. Black holes also have entropy, a measure of disorder or the number of possible internal states. Jacob Bekenstein proposed in 1972, before Hawking's radiation discovery, that black holes must have entropy proportional to their event horizon's surface area. This is called Bekenstein-Hawking entropy, and it's enormous compared to ordinary objects. For a solar mass black hole, the entropy is about 10 to the 54th power in natural units, vastly larger than the entropy of the Sun itself or any normal stellar object. This suggests black holes are the maximum entropy objects possible for a given mass. They represent the most disordered state matter can achieve. The fact that entropy is proportional to surface area rather than volume is profound and hints at deep principles about quantum gravity and information storage in spacetime. It suggests that information in a region might be encoded on its boundary, an idea that evolved into the holographic principle, which proposes that the information content of any region of space can be described by a theory living on that region's boundary. Black hole thermodynamics obeys laws analogous to classical thermodynamics, but with temperature and entropy defined by horizon properties. As our exploration concludes, we stand metaphorically at the event horizon, gazing both outward at all we've learned and inward toward mysteries that remain. Black holes, from violent birth in stellar death to silent evaporation across eons, embody nature's extremes and reveal physics' depths. We've traced the journey. Massive stars collapsing catastrophically, matter compressing beyond neutron degeneracy, space-time curving so severely that event horizons form. We've explored the geometry inside time and space exchanging roles, all paths leading to the singularity. We've seen how black holes grow through accretion and mergers, shaping galaxy evolution through feedback. We've discovered that black holes are not eternal prisons but thermodynamic objects with temperature and entropy, slowly evaporating through Hawking radiation. Given enough time beyond imagination, even supermassive black holes return their substance to the universe as thermal radiation, completing cycles that began with stellar birth. We've confronted deep puzzles, the information paradox, the nature of singularities, the relationship between quantum mechanics and gravity. These puzzles persist, marking frontiers where current physics meets its limits, where new theories are needed. We've seen how black holes connect to everything, to galaxy formation, to thermodynamics, to quantum field theory, to cosmology. They appear in mathematics, physics, astronomy, philosophy, art. They challenge our concepts of space, time, causality, information, existence. Yet despite all we've learned, the horizon remains. Beyond it lies the interior, forever hidden from external observers. At the center lies the singularity, where our equations break down and our understanding fails. Black holes keep secrets, holding knowledge we may never fully access. We end where we began, with wonder at the abyss. Black holes, from their birth in the violent collapse of dying stars to their final evaporation across timescales beyond comprehension, represent both ending and transformation, darkness and revelation, known and unknown. They are called black holes because no light escapes them, yet they've illuminated profound truths about reality. From Schwarzschild's first solution to Einstein's equations, through decades of theoretical development, to observations confirming their existence and properties, to Hawking's discovery of their radiation, to gravitational wave detections and direct imaging, each step has deepened understanding. Black holes teach us that time is relative, that space curves, that information might have physical substrate, that quantum mechanics and gravity intertwine at fundamental levels. They teach us humility. There are regions of reality forever beyond our direct observation, limits to knowledge built into nature's structure. Yet they also teach us capability. From our small planet, using mathematics and observation, we've mapped the geometry of spacetime near black holes, calculated their evolution over cosmic time, detected their mergers across billions of light years, and photographed their shadows. Human intelligence, for all its limitations, can grasp phenomena operating at scales utterly beyond direct experience. As you drift towards sleep, imagine standing at the edge of the event horizon, looking back at the universe you know. Stars shine in the distance. Time flows normally here, but ahead lies the boundary. Cross it and you enter a realm where all our normal concepts transform, where time becomes space, where all futures lead to one point, where physics itself remains mysterious. The abyss beckons eternally. Black holes persist, from birth to evaporation, as nature's deepest mysteries made manifest. In darkness we find light, in endings, transformations, in the abyss, wonder. The final moments of a black hole's evaporation are among the most extreme events theoretical physics can describe. As the black hole shrinks below atomic scales, below nuclear scales, approaching the Planck scale, our understanding breaks down. We enter a realm where both quantum mechanics and general relativity are crucial, but we lack a complete theory uniting them. At Planck mass, about 22 micrograms, the black hole size approaches the Planck length, 10 to the minus 35 meters, the smallest meaningful length in physics. At this scale, spacetime itself becomes quantum, fluctuating wildly. The distinction between spacetime and matter blurs. The black hole is no longer a classical object described by smooth geometry, but a quantum entity defying conventional description. The temperature at this stage is the Planck temperature, about 10 to the 32nd power Kelvin. At such temperatures, particle energies exceed anything achievable in accelerators by factors of trillions. All forces unify. All particles become indistinguishable. The black hole radiates a democratic spray of every particle type allowed by physics, including potentially undiscovered particles. The final burst releases the remaining mass energy in a fraction of a second. The power output in these final moments exceeds anything in the observable universe except perhaps the Big Bang itself. If we could witness this, and we could not survive proximity, we would see a flash brighter than supernovae, compressed into a point smaller than atoms. Then silence. The black hole is gone. The space-time curvature smooths out. Only radiation remains, dispersing into space, carrying away the black hole's final energy and, perhaps, encoded in some way we don't understand, the information about everything that ever fell in. The black hole has evaporated. The radiation has dispersed. What happened to the information? Every quantum state of every particle that fell into the black hole over its lifetime, where did that information go? If the information is truly lost, quantum mechanics is violated, and physics as we know it breaks down. If the information survives, encoded somehow in the Hawking radiation, then we need a mechanism for that encoding, and we must understand how quantum information escapes from behind an event horizon. Several proposals attempt to resolve this paradox. One suggests information is gradually encoded in correlations within the Hawking radiation. The radiation is not perfectly thermal, but contains subtle patterns preserving the information about what fell in. This encoding must be extraordinarily subtle, since Hawking radiation appears thermal to very high precision. Another proposal involves black hole complementarity, the idea that whether information is lost or preserved depends on the observer's perspective. An observer falling into the black hole carries information past the horizon and to the singularity. An outside observer sees that same information encoded in the Hawking radiation. Both descriptions are valid in their reference frames, with no contradiction because no single observer can verify both. More radical ideas suggest the horizon itself is not smooth but has structure, a firewall of high-energy particles that destroys anything approaching. This violates the equivalence principle's expectation that nothing special happens locally at the horizon of a large black hole, but it might preserve information by preventing it from truly entering. String theory offers another perspective through the holographic principle, suggesting all information about the black hole interior is encoded on the horizon's two-dimensional surface. When the black hole evaporates, this information is released in the radiation. Not all black holes form from stellar collapse. In the early universe, during the first seconds after the Big Bang, conditions might have allowed the formation of primordial black holes created directly from density fluctuations in the primordial plasma without requiring stars. If regions of space were slightly denser than average by sufficient amounts, their gravity could overcome pressure, causing them to collapse directly into black holes. These primordial black holes could have a wide range of masses, from far below stellar mass to supermassive, depending on the size and density of the collapsing region. Small primordial black holes are particularly interesting. A primordial black hole with initial mass around 10 to the 11th kilograms, about the mass of a small mountain, would be evaporating through Hawking radiation right now, after 13.8 billion years. Smaller ones would have already evaporated. Larger ones remain today. If primordial black holes exist, they could contribute to dark matter, the mysterious substance comprising 85% of the universe's matter. Small primordial black holes, too small to accrete much matter and too far from stars to be easily detected, could be drifting through galaxies unnoticed, revealing themselves only through gravitational effects. Detecting primordial black holes is challenging. Gravitational microlensing can reveal them if they pass between us and distant stars. If small primordial black holes are evaporating now, they should produce detectable gamma-ray bursts. Surveys searching for these signatures have constrained but not ruled out significant primordial black hole populations. The discovery of primordial black holes would be revolutionary, providing windows into the early universe's conditions and potentially solving the dark matter mystery. Current evidence neither confirms nor rules out their existence. If extra dimensions exist, as some theories like string theory propose, black holes could form at much lower energies than normally required. These hypothetical micro-black holes could potentially be created in high-energy particle collisions, like those in the Large Hadron Collider. Standard physics says creating black holes requires compressing matter to the Planck scale, which requires energies far beyond any accelerator. But if extra dimensions exist and are large enough, gravity becomes much stronger at small scales, and the energy threshold for black hole formation drops dramatically. When the LHC began operating, some wondered if it might create micro-black holes. If so, these black holes would be tiny, far smaller than atoms, and would evaporate instantly through Hawking radiation, existing for only 10 to the minus 27 seconds. They would pose no danger, evaporating long before interacting with any significant amount of matter. Despite searches, no evidence of micro-black hole production has been found at the LHC. This doesn't disprove extra dimensions, it constrains their properties, suggesting that if they exist, they're smaller or configured differently than some theories predicted. If micro-black holes could be created and studied, they would provide invaluable tests of quantum gravity. Their evaporation process, predicted by Hawking's theory, could be observed directly. Their properties would reveal information about extra dimensions and the fundamental structure of spacetime at the smallest scales. The absence of cosmic ray-induced micro-black hole production in Earth's atmosphere also constrains theories. Cosmic rays with far higher energies than the LHC regularly strike the atmosphere. If micro-black holes formed easily, we should see evidence. The fact that Earth hasn't been consumed by such black holes over billions of years suggests stringent limits. The extreme curvature of spacetime near black holes leads to fascinating possibilities, including theoretical connections to time travel. Rotating black holes, described by the Kerr solution, have particularly unusual properties that, mathematically at least, permit strange causal structures. Inside a rotating black hole, the singularity is a ring rather than a point. The mathematics of the Kerr solution suggests that if you could pass through this ring singularity without being destroyed, you might emerge into a different region of spacetime, perhaps another universe or perhaps another time in our own universe. These solutions are called closed time-like curves, paths through spacetime that loop back on themselves, allowing travel to one's own past. The Kerr solution contains such curves near the ring singularity. If they're traversable, time travel becomes possible in principle. However, most physicists believe these features are mathematical artifacts rather than physical realities. The interior of a rotating black hole is likely unstable. Perturbations, any slight deviation from perfect symmetry, probably cause the interior structure to change radically, perhaps forming a singularity that blocks passage through the ring. Even if the geometry were stable, passing through requires surviving the journey to the inner horizon and the ring singularity itself. Tidal forces would be enormous. The singularity represents a region where spacetime curvature becomes infinite, where known physics breaks down. Surviving passage seems impossible without invoking physics beyond general relativity. Moreover, time travel to the past creates paradoxes. If you could travel back and prevent your own time travel, what happens? Such paradoxes suggest nature has mechanisms preventing closed time-like curves from being traversable, even if the mathematics allows them. Stephen Hawking proposed a chronology protection conjecture that physical laws prevent time travel to the past. Related to black holes are wormholes, hypothetical tunnels through space-time connecting distant regions or even different universes. While distinct from black holes, wormholes share mathematical similarities and connections in the solutions to Einstein's equations. The simplest wormhole solution, the Einstein-Rosen bridge, emerges from the Schwarzschild black hole solution. Mathematically, the geometry of a non-rotating black hole can be extended beyond the singularity to another exterior region, another asymptotically flat spacetime. The two regions connect through a throat, forming a bridge. However, this bridge is non-traversable. Anything entering from one side cannot reach the other side before the throat collapses. The Einstein-Rosen bridge exists only momentarily in the geometry before the two regions pinch off from each other. Cannot serve as a shortcut through space. To create a traversable wormhole, one allowing travel from one region to another, requires exotic matter with negative energy density. Such matter would violate the energy conditions that normal matter obeys, creating repulsive gravity to hold the wormhole throat open against the tendency to collapse. Quantum field theory allows temporary negative energy densities through the Casimir effect and other phenomena, but sustaining them in the quantities and configurations needed for macroscopic wormholes seems impossible with known physics. This doesn't prove wormholes cannot exist, but it suggests they require physics beyond our current understanding. If traversable wormholes exist and connect regions separated in time as well as space, they could enable time travel with all the associated paradoxes. As with closed time-like curves near rotating black holes, most physicists suspect nature prevents wormholes from serving as time machines, though the exact mechanism remains uncertain. Black holes are not isolated curiosities but central players in cosmic evolution. Supermassive black holes at galaxy centers profoundly influence their host galaxies' development, regulating star formation and shaping galactic structure through feedback processes. When gas accretes onto a supermassive black hole, the energy released heats surrounding gas to millions of degrees. This hot gas can be expelled in powerful winds or jets, preventing the gas from cooling and forming stars. In this way, black holes regulate their own growth and their galaxy's star formation. This feedback explains the observed correlation between black hole mass and galactic bulge properties. As galaxies evolve, their central black holes grow through accretion and mergers. The growing black hole releases energy that affects the surrounding gas. Eventually, the feedback becomes strong enough to quench star formation, and both black hole and galaxy growth slow. Without black hole feedback, theoretical models produce galaxies that are too massive with too many stars. The most massive galaxies would continue forming stars indefinitely, growing far larger than observed. Black hole feedback provides the thermostat that regulates galaxy growth, explaining why the most massive galaxies are red and dead, dominated by old stars with little ongoing star formation. Galaxy mergers bring supermassive black holes together. When two galaxies merge, their central black holes spiral toward each other, eventually forming a binary black hole system. These binaries emit gravitational waves, slowly losing energy and angular momentum. After millions of years, the black holes merge, creating a single, more massive black hole. This hierarchical growth through mergers contributes to building the supermassive black holes we observe. Each galaxy merger potentially adds mass to the central black hole, gradually building monsters containing billions of solar masses over cosmic time. Looking far into the future, beyond the era of stars and galaxies, beyond even the era of stellar remnants and dead galaxies, black holes will dominate the universe's mass and energy. This is the black hole era, beginning perhaps 10 to the 40th power years from now, when most ordinary matter has been consumed or dispersed. By this time, star formation will have ceased. All stars will have burned out, leaving behind white dwarfs, neutron stars, and black holes. Galaxies will have long since dispersed through dynamical interactions and cosmic expansion. The universe will be cold, dark, and sparse. A thin soup of radiation, isolated stellar remnants, and black holes. Black holes will continue growing slowly through occasional captures of wandering matter and through rare mergers with other black holes. But primarily, they will wait. Their temperatures are far below the cosmic background radiation's temperature, which itself has cooled through expansion to near absolute zero. The black holes absorb more energy from the background than they emit through Hawking radiation. Eventually, after about 10 to the 60th power years, even the longest-lived stellar mass black holes will begin evaporating faster than they accrete. The cosmic background radiation, diluted by expansion, will drop below the black hole's Hawking temperature. From this point forward, black holes shrink. Supermassive black holes evaporate far more slowly. A billion solar mass black hole won't even begin significant evaporation for 10 to the 94th power years. But eventually, inevitably, they too will evaporate. One by one, over timescales that dwarf all previous cosmic history, the black holes will vanish in final bursts of radiation. After the last black hole evaporates, the universe will contain only dilute radiation and perhaps stable particles like photons, neutrinos, and electrons, separated by ever-increasing distances. Even as black holes slowly evaporate over unimaginable timescales, the universe itself continues to evolve under the influence of dark energy, the mysterious force driving the universe's accelerated expansion. Dark energy will shape the cosmos's ultimate fate just as profoundly as black holes. Dark energy behaves as though it has negative pressure, causing space to expand at an accelerating rate. As the universe expands, matter and radiation dilute. Their density drops as they spread through larger volumes. But dark energy density remains constant. With each passing eon, dark energy becomes increasingly dominant compared to all other forms of energy. This accelerating expansion has profound consequences for the distant future. Galaxy clusters, already gravitationally bound, will remain together. But unbound structures will separate ever faster. Eventually, all galaxies not in our local group will recede beyond the cosmic horizon, the distance beyond which light can never reach us due to expansion. In perhaps 100 billion years, intelligent observers in our galaxy would see a universe vastly emptier than we see today. Most galaxies visible to us now will have receded beyond the horizon, their light redshifted to undetectability. The cosmic microwave background will have cooled and redshifted beyond detection. Future observers might not be able to deduce that a Big Bang occurred or that other galaxies exist. This expansion continues indefinitely. The observable universe shrinks to just our local group of gravitationally bound galaxies. Eventually, even these galaxies merge into a single large galaxy containing all the stars, stellar remnants, and black holes that were once spread across our local cluster. Dark energy's dominance means that even as black holes evaporate over 10 to the 100th power years and beyond, the universe keeps expanding, growing ever colder, ever emptier, ever darker. If dark energy is not constant but instead grows stronger over time, a possibility some models of dark energy allow, the universe might end not in a cold, dark whimper but in a catastrophic tearing apart of all structures. This is called the Big Rip. In the Big Rip scenario, dark energy's repulsive effect increases without bound. Initially, it overcomes the expansion's deceleration, causing acceleration, what we observe today. But if it continues growing, it eventually overcomes not just cosmic expansion's tendency to slow, but the forces binding galaxies, stars, planets, molecules, and even atoms. The timeline for the Big Rip depends on how rapidly dark energy strengthens. In some models, it could occur within 20 billion years, sooner than many stellar mass black holes would naturally evaporate. In others, it takes longer but remains inevitable. As the Big Rip approaches, galaxy clusters first unbind. Then individual galaxies are torn apart, their stars scattering into intergalactic space. Then, a few months before the end, stars and planets are ripped from their orbits. Then, in the final minutes, planets themselves are torn apart. Then molecules, then atoms, then atomic nuclei, and finally, in the ultimate moment, even spacetime itself is torn apart. Black holes would not be immune. As dark energy grows strong enough to overcome gravitational binding at all scales, even event horizons would be disrupted. The Big Rip would tear spacetime itself apart, ending the universe in a singularity of infinite expansion, the opposite of the Big Bang's singularity of infinite compression. Current observations suggest dark energy is consistent with a cosmological constant, unchanging over time, which does not lead to a Big Rip. But we cannot yet rule out models where dark energy evolves. The universe's ultimate fate remains uncertain. As we've discussed, Hawking radiation arises from quantum effects near the event horizon. But the full quantum behavior of black holes remains mysterious, touching the deepest unsolved problems in theoretical physics. What happens to space-time and matter at quantum scales near and inside black holes? Quantum field theory in curved space-time, the framework Hawking used, treats space-time as classical, curved by gravity according to general relativity, while quantum fields propagate through this curved space-time. This approximation works far from extreme conditions. But near the singularity, where space-time curvature becomes infinite, or at the Planck scale, where quantum fluctuations of space-time itself become important, this approximation breaks down. We need quantum gravity, a theory describing space-time itself as quantum. Such a theory should resolve the singularity, replacing the infinite curvature predicted by classical general relativity with some finite quantum structure. It should also fully describe black hole microstates, the quantum states corresponding to the black hole's entropy. String theory offers one approach. In string theory, black holes are collections of strings and branes in particular configurations. The black hole's entropy counts the number of possible string configurations matching the hole's mass and charge. This provides a microscopic explanation for Bekenstein-Hawking entropy and suggests information is preserved in string degrees of freedom. Loop quantum gravity offers another approach. It suggests spacetime is quantized, made of discrete units at the Planck scale. The singularity is replaced by a region of maximum curvature where quantum geometry prevents infinite compression. Black hole entropy arises from counting possible quantum geometries of the horizon. Both approaches remain incomplete, and neither has made predictions we can test observationally. Quantum gravity remains theoretical physics' greatest unsolved problem. In 2012, physicists proposed a provocative idea that challenged our understanding of black holes: the Firewall Paradox. This paradox suggests that the event horizon might not be the smooth, uneventful boundary predicted by general relativity, but rather a wall of high-energy particles that incinerates anything approaching. The paradox arises from attempting to reconcile three seemingly incompatible principles. Quantum mechanics requires information to be preserved. Hawking's calculation shows radiation from black holes is thermal and carries information only through subtle correlations. And the equivalence principle requires that nothing special happens locally at the event horizon of a sufficiently large black hole. If information escapes in Hawking radiation through quantum entanglement, particles in the early radiation must be entangled with particles in late radiation. Otherwise, information cannot be gradually released. But these particles are also entangled with their partners that fell into the black hole. The standard picture of Hawking radiation involves entangled pairs with one partner escaping and one falling in. Quantum mechanics forbids a particle being maximally entangled with two different systems. This is called monogamy of entanglement. Something must give. The firewall hypothesis suggests the infalling partner is destroyed at the horizon, breaking its entanglement and allowing the outgoing particle to be entangled with future radiation. But this violates the equivalence principle. An observer falling into a large black hole should experience nothing unusual at the horizon. The tidal forces there are negligible. If a firewall exists, it would be a dramatic, locally detectable feature. This paradox has generated intense debate. Proposed resolutions include modifications to quantum mechanics, violations of the equivalence principle, or the idea that no single observer can verify the paradox because doing so would require impossible measurements. The holographic principle, inspired by black hole thermodynamics, suggests that the information content of any region of space is encoded on that region's boundary rather than throughout its volume. This counterintuitive idea has profound implications for our understanding of reality. The principle originates from the Bekenstein-Hawking formula for black hole entropy, which is proportional to the event horizon's area rather than the volume inside. This suggests that the maximum information that can be contained in any region is determined by the boundary's area, not the volume like a hologram, which encodes three-dimensional information on a two-dimensional surface. Gerard T. Hooft and Leonard Susskind generalized this idea beyond black holes, proposing that it applies to any region of space. The information describing everything in a volume is equivalent to information encoded on the bounding surface. Our three-dimensional world might be a holographic projection from a two-dimensional surface. String theory provides a concrete realization through the ADS/CFT correspondence, discovered by Juan Meldacena. This correspondence relates a gravitational theory in a higher-dimensional anti-de Sitter space to a quantum field theory on the boundary of that space. Gravity in the bulk is equivalent to physics on the boundary without gravity. Though ADS/CFT applies to a spacetime unlike our universe, it demonstrates that holographic principles can work mathematically. It suggests that quantum gravity might be completely described by a theory without gravity in one fewer dimension, a remarkable simplification. For black holes, holography suggests all information about the interior is encoded on the horizon. When the black hole evaporates, this information is released in the Hawking radiation. The interior might not even exist in the same sense we normally think. It might be a derived description of physics happening on the horizon. If the multiverse exists, if our universe is one of many, black holes might behave differently in universes with different physical laws or constants. Exploring these possibilities reveals what's essential to black hole formation and what depends on our particular cosmic environment. In a universe with a stronger gravitational constant, black holes would form more easily and be more common. Stars would be smaller and shorter-lived, and the mass threshold for black hole formation would be lower. In a universe with much weaker gravity, black holes might never form, stars might not achieve the densities needed for supernova collapse, or the collapse might always halt at neutron star densities. If the speed of light were different, the Schwarzschild radius formula would change, affecting when and how black holes form. If quantum mechanics worked differently, if the Planck scale were much larger, Hawking radiation would be stronger, and small black holes might evaporate rapidly enough to be observable. In universes with different numbers of spatial dimensions, black hole properties change dramatically. In 2 spatial dimensions, black holes cannot exist as we know them. In 4 or more spatial dimensions, black hole horizons have different geometries, and the relationship between mass and horizon size differs. Hawking radiation depends on dimensionality. Black holes in higher dimensions evaporate faster. Some eternal inflation models suggest different bubble universes have different effective laws of physics, different particles, forces, or constants. In most of these bubbles, conditions might not allow complex structures. But in the rare bubbles where structures form, black holes might be among the most universal features, their existence depending only on gravity and the possibility of mass concentration. The study of black holes in hypothetical universes reveals they are robust consequences of general relativity. The next decades will transform our understanding of black holes through new observations and technologies. Gravitational wave astronomy, in its infancy, will mature into a powerful tool for studying black holes across cosmic history. Current gravitational wave detectors like LIGO and Virgo detect stellar mass black hole mergers within a few billion light-years. Upgrades will increase sensitivity, detecting mergers farther away, effectively looking deeper into the past. We'll observe black holes from earlier cosmic epochs, learning how black hole populations evolved over billions of years. Space-based gravitational wave detectors, like the planned LISA mission, will detect supermassive black hole mergers across the observable universe. These mergers occur when galaxies merge, bringing their central black holes together. LISA will hear these events, providing insights into galaxy evolution and supermassive black hole growth. The Event Horizon Telescope continues improving. Adding more radio telescopes to the global network will sharpen images of black hole shadows. We'll image more black holes, different masses, different spins, different accretion rates, testing general relativity's predictions in strong gravity regimes. Future telescopes will study accretion physics in unprecedented detail. X-ray observatories will map how matter falls into black holes, how jets form, how magnetic fields behave in extreme gravity. These observations will constrain models of accretion disk physics and test predictions about black hole spin effects. Perhaps most excitingly, if Hawking radiation is detectable, if primordial black holes are evaporating now, gamma-ray observatories might detect the telltale bursts. Such detection would confirm Hawking's prediction and open a new window on quantum gravity effects. Even non-detection would constrain primordial black hole abundance and properties, informing cosmology and dark matter research. Black holes represent nature's most extreme objects in almost every measurable quantity. Understanding just how extreme they are helps us grasp their significance in physics and cosmology. Consider density. A stellar mass black hole of 10 solar masses has a Schwarzschild radius of about 30 kilometers. The average density within this radius, if we calculate mass divided by volume, though this is a classical calculation that breaks down near the horizon, is roughly 10 to the 16th power kilograms per cubic meter. This is about the density of an atomic nucleus, or about 100 trillion times denser than water. But for supermassive black holes, average density decreases with mass. A billion solar mass black hole has an average density less than water, about 1 kilogram per cubic meter. You could, in principle, swim through the event horizon of such a black hole without immediately noticing, though you'd be doomed once inside. This counterintuitive result arises because the Schwarzschild radius grows linearly with mass while volume grows with radius cubed. Gravity at the event horizon also scales inversely with mass. For a solar mass black hole, tidal forces at the horizon are lethal, about 100 million times Earth's surface gravity per meter. But for a billion solar mass black hole, tidal forces at the horizon are only a few times Earth's gravity per meter, survivable at least briefly. Time dilation near black holes is extreme. At 1 Schwarzschild radius above the horizon, time passes at about 40% the rate of distant observers. At 0.1 Schwarzschild radii above the horizon, time nearly stops from an outside perspective. 1 second for the nearby observer corresponds to years for distant observers. These extremes make black holes natural laboratories for testing physics in conditions impossible to replicate otherwise. Black holes raise profound philosophical questions extending beyond physics into metaphysics and the nature of consciousness. When matter falls into a black hole, when information potentially vanishes behind an event horizon, what does this mean for concepts like existence, knowledge, and observation? Consider an observer falling into a black hole. From their perspective, they cross the horizon and continue toward the singularity. Their consciousness, if it survives tidal forces, persists. They experience continuous existence. But from an outside observer's perspective, they never cross, forever frozen at the horizon, redshifted into invisibility. Both descriptions are valid in their reference frames. The infalling observer experiences crossing. The outside observer never sees crossing. Does the infalling observer's post-horizon experience exist for the outside universe? This question touches the nature of existence itself, whether something is real only if observable or real independent of observation. The information paradox connects to consciousness in subtle ways. If conscious observers make measurements that collapse quantum states, and if information about those states falls into black holes, does the information truly exist in some abstract sense, or is it only real when observable? Different interpretations of quantum mechanics give different answers. Some thinkers speculate about connections between black holes and consciousness itself. Roger Penrose has proposed that quantum gravity effects in the brain might be relevant to consciousness. While highly speculative and controversial, such ideas illustrate how black holes, as windows into quantum gravity, touch the deepest questions about mind and matter. Black holes remind us that reality has features fundamentally beyond human intuition. We evolved to navigate a world of medium-sized objects at moderate speeds. Black holes exist in regimes where space, time, matter, and causation behave nothing like our exp. Black holes have played crucial roles in shaping the universe's evolution from the early cosmos to today. Their influence extends far beyond their immediate vicinity, affecting galaxy formation, star formation rates, and even the large-scale structure of the cosmos. In the early universe, the first black holes, whether from population 3 stars or direct collapse, began the process of building supermassive black holes. These early black holes accreted aggressively, growing rapidly and powering quasars that ionized hydrogen throughout the universe during the epoch of reionization. Their radiation helped transform the universe from neutral to ionized, enabling light to travel freely. As galaxies assembled through mergers, their central black holes merged too, growing hierarchically. The feedback from these accreting black holes regulated star formation in their host galaxies. Without black hole feedback, the most massive galaxies would contain far more stars than observed. Black holes acted as cosmic thermostats. Black holes concentrate matter and energy, In galaxy clusters, they heat the intracluster medium through jets and radiation, preventing this gas from cooling and forming stars. This heating explains why galaxy clusters contain so much hot gas but form relatively few stars. The central black holes prevent runaway star formation. Black holes also drive cosmic recycling. Material falling into black holes releases energy as radiation and jets. This energy heats surrounding gas, sometimes expelling it from galaxies in winds. Later, this enriched gas can cool and fall back, forming new generations of stars. Black holes thus regulate the pace and efficiency of star formation across cosmic time. Looking forward, black holes will increasingly dominate the universe's mass. After stars cease forming, after stellar remnants fade, black holes will be the last massive objects, slowly evaporating over timescales exceeding the current age of the universe by factors of trillions. Black holes have the highest entropy of any object for a given mass, making them intimately connected to time's arrow, the fundamental asymmetry between past and future. Understanding this connection reveals deep relationships between gravity, thermodynamics, and the nature of time itself. Entropy measures disorder, or more precisely, the number of microscopic configurations consistent with macroscopic properties. A low-entropy state has few possible configurations. It's ordered, organized, special. A high-entropy state has many possible configurations. It's disordered, generic, probable. The second law of thermodynamics states that entropy always increases. Systems evolve from special, unlikely states toward generic, probable states. This entropy increase defines time's arrow. We remember the past but not the future because memories are low-entropy records formed in a lower-entropy past. We see glasses shatter but never spontaneously reassemble because shattered states have far higher entropy than intact states. Time's arrow emerges from entropy's increase. Black holes fit naturally into this framework. When matter falls into a black hole, the entropy increases dramatically. The organized structure of a star or planet becomes part of the black hole's featureless horizon. The Bekenstein-Hawking entropy quantifies this increase. Proportional to the horizon area, it vastly exceeds the entropy of the matter that formed the black hole. As black holes evaporate via Hawking radiation, entropy continues increasing. The radiation carries away entropy, eventually exceeding the black hole's original entropy. The final state, dispersed thermal radiation, has higher total entropy than the initial state. Throughout the process, entropy never decreases, consistent with the second law. Some physicists propose that black holes are essential to time's arrow on cosmic scales. In the far future, when black holes dominate the universe's mass, their evaporation will be the primary entropy increased. In classical general relativity, the singularity is a point or region where spacetime curvature becomes infinite, where density becomes infinite, where all known laws break down. It's not a place in space, but a moment in time for anything falling in, the inevitable endpoint of all world lines crossing the event horizon. But most physicists believe this classical description is incomplete. Just as classical electromagnetism predicted infinite energies for atoms until quantum mechanics resolved the issue, classical general relativity's singularities likely signal the need for quantum gravity. At the extreme densities near the singularity, quantum effects should dominate. What replaces the singularity in quantum gravity? Different theories offer different answers. String theory suggests strings cannot be compressed below a minimum size, the string length. As matter approaches this scale, it doesn't continue collapsing but enters a different phase, possibly bouncing or transitioning to a different region of spacetime. Loop quantum gravity proposes that spacetime itself is quantized, discrete at the Planck scale. density and curvature cannot become infinite because space comes in finite chunks. The singularity is replaced by a region of maximum but finite curvature, possibly connecting to another region of spacetime through a quantum bounce. Other approaches suggest singularities might be replaced by exotic objects like gravistars, hypothetical configurations where extreme vacuum energy prevents complete collapse, or fuzzballs in string theory, where the black hole interior is filled with stringy degrees of freedom rather than empty space leading to a singularity. The singularity remains physics' great unknown, the ultimate frontier where our understanding ends. Black holes challenge our intuitive understanding of space itself. The extreme curvature near a black hole reveals that space is not a passive stage where events unfold but a dynamic entity that responds to matter and energy that can be stretched, compressed, torn, and perhaps even have topology. In ordinary experience, space seems flat and unchanging, a three-dimensional grid extending infinitely. But general relativity reveals space is curved by mass and energy. Earth curves space slightly, the sun more so, neutron stars dramatically. Black holes take this to the extreme, curvature so severe that space becomes unrecognizable. Inside the event horizon, the roles of space and time become interchanged in a mathematical sense. The direction toward the singularity is timelike. You move toward it inevitably as time passes, just as you move inevitably toward the future outside the black hole. You cannot remain at a fixed distance from the singularity any more than you can remain at a fixed time outside. This suggests that our familiar concepts of space and time are approximations, valid in weak gravity but breaking down in extreme conditions. Space and time are not fundamental but emergent, arising from something deeper, perhaps quantum entanglement or information as holographic principles suggest. Black holes might represent places where spacetime's topology is non-trivial. While we cannot see inside event horizons, the mathematics allows for exotic topologies, wormholes connecting distant regions, baby universes budding off from singularities, or spacetime with handles and holes. Whether these mathematical possibilities are physical realities remains unknown. The study of black holes thus becomes the study of spacetime itself, probing its limits, discovering its properties, learning what space and time truly are beneath the everyday appearances we navigate. Black holes have inspired numerous thought experiments revealing deep tensions and insights in physics. These Gedanken experiments, in Einstein's tradition, probe edge cases where our theories are tested to their limits. Consider the falling observer paradox. An observer falling into a black hole crosses the event horizon and continues toward the singularity from their perspective. But an outside observer never sees them cross. They see the infalling observer slow, redshift, and fade, approaching but never reaching the horizon. Both perspectives are correct in their reference frames. Does the experience beyond the horizon exist for the universe outside? This question has no clear answer in general relativity. Or consider the cloning paradox related to Hawking radiation. If information encoded in matter falling into a black hole later emerges in Hawking radiation, the information exists in two places, inside and outside. But quantum mechanics forbids perfect cloning of quantum states. Something must resolve this tension. Perhaps information is not truly cloned, or perhaps the interior and exterior descriptions are complementary rather than independent. The grandfather paradox applies if closed time-like curves exist near rotating black holes. Could you travel through a black hole to your own past and prevent your own time travel? Most physicists suspect nature prevents such paradoxes, either by making closed time-like curves non-traversable or by cosmic censorship, hypothesized principles preventing naked singularities or other pathologies that would violate causality. These paradoxes are not mere philosophical puzzles. They point to genuine tensions between quantum mechanics, general relativity, and thermodynamics, tensions that should guide us toward deeper theories. Resolving them likely requires quantum gravity, a theory we're still developing. The paradoxes keep physicists humble, reminding us how much we don't understand about reality's fundamental nature. Black holes introduce multiple forms of infinity into physics: infinite curvature at singularities, infinite time dilation at horizons, infinite tidal forces. Understanding how physics treats these infinities reveals the relationship between mathematics and physical reality. In mathematics, infinity is a well-defined concept with rigorous rules. But in physics, infinities often signal that a theory has reached its limits, that we're extrapolating beyond the domain where the theory applies. The infinities in black hole physics are likely such signals. The infinite curvature at the singularity doesn't mean spacetime actually becomes infinite there. It means general relativity, our theory of spacetime, breaks down. The equations produce infinity because they're being applied where they no longer work, at quantum scales where quantum gravity should take over. Similarly, the infinite time dilation at the event horizon is coordinate dependent. In Schwarzschild coordinates, one way of describing the spacetime, the time coordinate becomes infinite at the horizon. But in other coordinates, like Kruskal-Zachary's coordinates, time remains finite. The infinity is a feature of our description, not the physical reality. Infinite tidal forces near the singularity of a stellar mass black hole are again likely artifacts of classical theory. Quantum effects should cut off the divergence at some finite value, replacing the singularity with a quantum structure. Physics has encountered infinities before and resolved them through better theories. Classical electromagnetism predicted infinite self-energy for point charges, resolved by quantum electrodynamics and renormalization. Classical cosmology predicted infinite density at the Big Bang, likely to be resolved by quantum cosmology. The black hole infinities await similar resolution. Yet, infinities in mathematics remain useful idealizations. The properties of black holes depend on fundamental constants: the speed of light, the gravitational constant, Planck's constant. Exploring how black holes would differ if these constants had different values reveals what's essential and what's contingent about these cosmic objects. The Schwarzschild radius is proportional to mass and the gravitational constant, and inversely proportional to the speed of light squared. If light were slower, the Schwarzschild radius for a given mass would be larger. Black holes would form more easily. If gravity were stronger, the same smaller stars could collapse into black holes. Hawking temperature depends on all three fundamental constants: gravitational constant, speed of light, and Planck's constant. The temperature is inversely proportional to mass and directly proportional to the combination of constants that defines the Planck scale. This connection reveals that black hole evaporation is fundamentally a quantum gravitational phenomenon, requiring both quantum mechanics and gravity. In our universe, the Planck mass, the mass scale where quantum gravity becomes important, is about 22 micrograms, far smaller than stellar masses. This means stellar mass and larger black holes are well described by classical general relativity, with quantum effects negligible except over enormous timescales. But if Planck's constant were larger or the gravitational constant much different, quantum effects would be important even for macroscopic black holes. The dimensionless ratios between constants determine much of physics structure. For black holes, the ratio between the Schwarzschild radius and Compton wavelength, the quantum mechanical length scale for a given mass, is crucial. This ratio is enormous for stellar mass black holes, explaining why classical physics works. For Planck mass black holes, the ratio is unity, quantum and gravitational scales match, and neither can be ignored. Black holes captivate human imagination in ways few scientific concepts do. They appear in science fiction, art, philosophy, becoming symbols for the unknown, the terrifying, the sublime. Understanding this psychological resonance reveals something about human nature and our relationship with cosmic mystery. The name itself evokes fear and fascination. Black hole conjures images of cosmic drains, vortexes that swallow everything, ultimate endings. The older term frozen star was more descriptive but less evocative. Black hole, coined by John Wheeler in 1967, captured public imagination precisely because it suggested something absolute and final. Psychologically, black holes embody several primal fears and fascinations. They represent ultimate unknowability. We cannot see inside, cannot escape if we enter, cannot retrieve anything consumed. They represent inevitable doom. Once you cross the horizon, no power in the universe can save you. They represent annihilation, identity, structure, information, perhaps consciousness itself destroyed at the singularity. Yet they also fascinate precisely because they're extreme. Humans are drawn to extremes, the highest mountains, the deepest oceans, the furthest reaches of space. Black holes are the ultimate extreme, the most concentrated matter, the strongest gravity, the most warped spacetime. They represent the limits of physical possibility. In fiction, black holes serve as portals, as time machines, as cosmic obstacles, as weapons. These fictional uses rarely match reality but capture something true. Black holes are liminal objects, boundaries between the knowable and unknowable, natural and supernatural, science and speculation. The fact that black holes actually exist makes them more powerful as symbols. They're not fantasy but real features of our universe, validated by observation and mathematics. The abyss is not metaphorical but physical, and it stares back from the centers of galaxies. In the unimaginably distant future, after 10 to the 100th power years and beyond, black holes will have evaporated, leaving a universe transformed beyond recognition. Understanding this ultimate fate provides perspective on black holes' role in cosmic evolution and the nature of existence itself. After the last black hole evaporates, the universe contains only radiation, photons, neutrinos, and perhaps other stable particles, diluted by expansion to unimaginable sparseness. The average energy density approaches zero. The temperature approaches absolute zero asymptotically but never quite reaches it. The universe continues expanding, driven by dark energy if it remains constant, or undergoing some other fate if dark energy evolves. Either way, after black holes evaporate, no structures remain. No stars, no planets, no life, no complexity. Only simple particles separated by ever-growing distances. Some physicists speculate about quantum fluctuations even in this far future. Given infinite time, quantum mechanics allows arbitrarily rare events. Perhaps random fluctuations occasionally create brief structures, temporary assemblies of particles that exist for moments before dispersing. In the vast emptiness, such fluctuations might be the only events occurring. Another speculation involves Boltzmann brains, the idea that random fluctuations might occasionally create conscious observers spontaneously, without evolutionary history. In infinite time, such fluctuations become not just possible but inevitable. This raises paradoxes about the nature of observation and existence. If the multiverse is real, with eternal inflation continuously creating bubble universes, then even as our universe fades, others are being born. Black holes in those young universes are forming, accreting, evaporating. The cycle continues eternally on larger scales, even though individual universes have beginnings and endings. The far future, with its fading black holes, reminds us that all structures are. Our journey through black holes from birth to evaporation has revealed profound truths about nature. From the death of stars through supernova collapse, to the formation of event horizons where time stops and escape becomes impossible, to the deep connections between gravity, quantum mechanics, and thermodynamics revealed by Hawking radiation. We've learned that black holes are not exotic curiosities but fundamental features of a universe with gravity. Given sufficient mass and density, event horizons inevitably form. This is a mathematical certainty in general relativity. Black holes are not aberrations but natural endpoints of stellar evolution and growth of structure in the universe. We've learned that black holes are simpler than the matter that forms them. The No-Hair Theorem tells us that all complexity reduces to just mass and spin. Yet, paradoxically, black holes have the highest entropy. They are maximum complexity in thermodynamic terms while being maximum simplicity in geometric terms. We've learned that black holes connect disparate areas of physics. General relativity describes their geometry. Quantum field theory predicts their radiation. Thermodynamics emerges from their properties. Information theory confronts paradoxes at their boundaries. String theory and loop quantum gravity attempt to describe their singularities. Black holes are where fundamental physics converges. We've learned that black holes are not eternal. Hawking's insight transformed them from permanent cosmic prisons to temporary way stations. On timescales vastly exceeding the current age of the universe, even the largest black holes will evaporate, returning their mass energy to the cosmos as radiation. We've learned that black holes shape cosmic evolution. They regulate galaxy growth through feedback. They mark the endpoints of stellar evolution. They will dominate the universe's mass in the far future. They are integral to the cosmos, not peripheral. We have journeyed from the violent collapse of dying stars to the slow evaporation across timescales that dwarf the age of the universe. We have descended past event horizons into regions where time and space exchange roles, where the future becomes a place you cannot avoid. The singularity hidden at the heart of every black hole. Black holes remind us that the universe is stranger than our everyday experience suggests. Matter can collapse to infinite density. Time can stop. Information can vanish, or does it? Light itself cannot escape sufficiently strong gravity. These are not science fiction fantasies but mathematical consequences of general relativity, confirmed by observation. Yet even as black holes represent extremes of physics, they also represent extremes of beauty. The perfect geometry of the Schwarzschild solution, the elegant simplicity of the No-Hair Theorem, the profound connection between entropy and horizon area, the unexpected prediction of Hawking radiation uniting quantum mechanics, gravity, and thermodynamics. Black holes are aesthetic objects as much as physical ones. Standing at the edge of understanding, contemplating black holes, we confront deep questions. What is the nature of time? What is information? What happens at the boundary of quantum and gravitational regimes? How does our universe connect to others? If it does, what is ultimately real? These questions have no final answers yet, but pursuing them has expanded human knowledge immeasurably. From Schwarzschild's calculation in a war-torn world to the Event Horizon Telescope's image of M87's black hole, from Hawking's insight about radiation to ongoing debates about information preservation, each generation pushes understanding deeper. The abyss beckons still. Black holes, from their violent births to their final evaporation into quantum foam, remain among the universe's deepest mysteries. As our exploration of black holes concludes, we recognize patterns echoing across cosmic scales: birth, existence, death, and transformation. Black holes are not endpoints but way stations in the universe's eternal cycle of matter and energy. A massive star is born from collapsing gas clouds, shines for millions of years, then dies in supernova fury, birthing a black hole. The black hole grows by accretion, perhaps merges with others, persists for eons beyond human comprehension. Then, through Hawking radiation, it slowly returns its mass to the universe as thermal photons and particles. These particles disperse into space, eventually contributing to new clouds, new stars, continuing the cycle. This cycle operates on timescales ranging from microseconds to 10 to the 100th power years. The supernova collapse takes less than a second. The black hole might exist for times exceeding the universe's current age by factors of trillions. Yet ultimately, the cycle completes. Nothing is truly permanent. Even black holes, seemingly eternal prisons from which nothing escapes, eventually evaporate. The same patterns appear at other scales. Quantum particles emerge from vacuum fluctuations and annihilate back into vacuum. Stars form from gas and return gas to space. Galaxies merge and disperse. The universe itself began in a singularity and may end in heat death or some other fate. Creation and destruction, order and entropy, structure and decay. These rhythms pervade nature. Black holes epitomize these cycles at their most extreme. They represent maximum concentration of matter, maximum gravitational binding, maximum entropy, all the extremes of physics united in single objects. Then they dissolve, releasing everything back into the cosmic stream. Perhaps the singularity at a black hole center is itself a kind of beginning, not for our universe, but for some other structure we cannot observe. Throughout our journey, we've encountered a subtle theme: the relationship between observer and observed, between what exists and what can be known. Black holes challenge this relationship in profound ways that connect to deep questions in philosophy and physics. The event horizon creates an absolute observational boundary. What happens inside cannot be seen from outside. An observer who crosses to observe the interior can never report back. This is not a practical limitation but a fundamental one. Even in principle, with arbitrarily advanced technology, the interior remains forever hidden from external observers. This raises questions about the nature of existence. Does the interior exist in the same sense as the exterior? For the outside universe, everything about the interior is summarized by the black hole's mass, spin, and charge, 3 numbers. All other information is inaccessible. In what sense, then, does the interior's detailed structure exist? Different interpretations of quantum mechanics suggest different answers. In some interpretations, unobserved quantum states have indefinite properties. They're in superposition until measured. Does this mean the interior, forever unmeasurable from outside, remains in some kind of quantum limbo? The information paradox centers on similar issues. If information falling into a black hole is truly lost from the universe, unmeasurable, unrecoverable even in principle, does it still exist? Quantum mechanics suggests information cannot be destroyed, but general relativity seems to allow exactly that. The tension reveals gaps in our understanding. Perhaps the resolution involves recognizing that existence and observability are more deeply connected than classical physics suggests. Perhaps quantum mechanics teaches us that reality is relational. Things exist in relation to other things, through interactions and measurements. Throughout our journey, we've encountered a subtle theme: the relationship between observer and observed, between what exists and what can be known. Black holes challenge this relationship in profound ways that connect to deep questions in philosophy and physics. The event horizon creates an absolute observational boundary. What happens inside cannot be seen from outside. An observer who crosses to observe the interior can never report back. This is not a practical limitation but a fundamental one. Even in principle, with arbitrarily advanced technology, the interior remains forever hidden from external observers. This raises questions about the nature of existence. Does the interior exist in the same sense as the exterior? For the outside universe, everything about the interior is summarized by the black hole's mass, spin, and charge, 3 numbers. All other information is inaccessible. In what sense, then, does the interior's detailed structure exist? Different interpretations of quantum mechanics suggest different answers. In some interpretations, unobserved quantum states have indefinite properties. They're in superposition until measured. Does this mean the interior, forever unmeasurable from outside, remains in some kind of quantum limbo? The information paradox centers on similar issues. If information falling into a black hole is truly lost from the universe, unmeasurable, unrecoverable even in principle, does it still exist? Quantum mechanics suggests information cannot be destroyed, but general relativity seems to allow exactly that. The tension reveals gaps in our understanding. Perhaps the resolution involves recognizing that existence and observability are more deeply connected than classical physics suggests. Perhaps quantum mechanics teaches us that reality is relational. Things exist in relation to other things, through interactions and measurements. Black holes demonstrate the power and limits of mathematics in describing physical reality. They emerged first as mathematical solutions to Einstein's equations, seemingly exotic curiosities. Decades passed before observations confirmed these mathematical abstractions correspond to real objects. This pattern, mathematics predicting phenomena later observed, recurs throughout physics. Maxwell's equations predicted electromagnetic waves before radio waves were detected. Dirac's equation predicted antimatter before positrons were discovered. Einstein's field equations predicted gravitational waves a century before LIGO detected them. Black holes follow this pattern, existing first in equations before being found in nature. Why is mathematics so unreasonably effective at describing nature, as Eugene Wigner famously asked? Black holes offer a particularly striking example. The mathematics of general relativity, dealing with abstract concepts like curved spacetime and geodesic motion, accurately predicts that objects exist where infinite spacetime curvature hides behind event horizons from which nothing escapes. The agreement between mathematical prediction and physical observation is precise. Yet mathematics also reveals its limits at black hole singularities. The equations produce infinities, suggesting they're being pushed beyond their domain. Mathematics signals its own breakdown, pointing toward new theories needed to describe reality completely. This interplay between mathematics and physics suggests deep relationships between logical structure and physical existence. Some physicists, like Max Tegmark, propose that mathematical existence and physical existence are the same, that our universe is a mathematical structure, and all mathematical structures exist in some sense. Black holes, as nearly pure geometric objects defined by simple equations, support this perspective. Others maintain that mathematics describes reality without being identical to it, that physical EXI. Two figures dominate black hole physics: Albert Einstein, whose general relativity predicted them, and Stephen Hawking, who revealed they're not entirely black. Their work, separated by 6 decades, transformed our understanding of gravity, space-time, and the universe. Einstein's general relativity, published in 1915, reimagined gravity not as a force but as spacetime curvature. Mass and energy curve spacetime. Objects follow geodesics through this curved geometry. This elegant framework made stunning predictions: light bending around the sun, Mercury's orbital precession, gravitational time dilation, and ultimately, black holes. Ironically, Einstein himself doubted black holes could exist. In 1939, he published a paper arguing that stellar collapse couldn't produce singularities. Nature would find ways to prevent complete collapse, he believed. This was one of Einstein's rare major errors. Observations have since confirmed black holes are abundant. Stephen Hawking, working in the 1970s, combined quantum field theory with general relativity to discover black hole radiation. His calculations showed that what seems eternal and unchanging from classical gravity is actually dynamic and temporary from quantum physics. Black holes evaporate. This insight connected gravity, thermodynamics, and quantum mechanics in unexpected ways. Hawking's work revealed tensions between quantum mechanics and general relativity, particularly the information paradox. These tensions remain unresolved, pointing toward needed developments in quantum gravity. Hawking believed information is preserved somehow, changing his position from earlier views that it might be lost. Both Einstein and Hawking shared qualities beyond intellect: deep physical intuition, mathematical skill, and persistence in pursuing understanding despite obstacles. Einstein revolutionized physics despite initial academic struggles. Hawking made profound discoveries despite debilitating illness. Black holes exemplify how different branches of knowledge converge on profound truths. Physics, mathematics, philosophy, even art and literature, all find meaning in these cosmic objects. Understanding black holes requires and illuminates multiple ways of knowing. Physics provides the foundation: general relativity for large-scale geometry, quantum mechanics for Hawking radiation, thermodynamics for entropy, particle physics for what happens to matter. No single physics subfield suffices. Black holes demand integration across domains. Mathematics offers the language and structure. Differential geometry describes curved spacetime. Topology addresses event horizons and singularities. Quantum field theory in curved spacetime requires sophisticated mathematics connecting geometry and quantum mechanics. Information theory enters through the information paradox. Philosophy confronts questions mathematics cannot answer. What does it mean for information to be lost? How do we interpret divergent perspectives of infalling and distant observers? What is the nature of existence for regions forever unobservable? These questions bridge physics and metaphysics. Even aesthetics plays a role. Scientists describe black hole solutions as beautiful or elegant, aesthetic judgments reflecting deep symmetries and simplifications. The unexpected simplicity of the No-Hair Theorem, the elegant connection between area and entropy, the profound implications of Hawking radiation, these have aesthetic dimensions appreciated by practitioners. Literature and art explore black holes symbolically, representing the unknown, the terrifying, the sublime. While these explorations are not scientific, they engage aspects of human experience: awe, fear, wonder that dry technical descriptions miss. Black holes mean something beyond their physics, resonating with human consciousness contemplating cosmic mystery. This convergence suggests that understanding reality requires multiple perspectives. Despite a century of study, fundamental questions about black holes remain unanswered. These open questions define research frontiers and hint at how much we have yet to learn. The information paradox persists as perhaps the deepest puzzle. Where does information go when matter falls into black holes? How is it preserved if black holes evaporate? Proposed solutions remain speculative, awaiting experimental tests or theoretical breakthroughs. The nature of singularities remains unknown. Does quantum gravity resolve them into finite structures? Or do genuine singularities exist in nature? If resolved, what replaces them? Quantum foam bounces to other regions, something entirely different. The relationship between black holes and quantum gravity is central but unclear. Black holes should be key to understanding quantum gravity, yet we lack a complete theory. String theory and loop quantum gravity offer approaches, but neither is confirmed observationally. Do primordial black holes exist? If so, do they constitute some or all of dark matter? Could we detect their Hawking radiation if they're evaporating? These questions connect black hole physics to cosmology and particle physics. How do supermassive black holes form so early in cosmic history? Observations show billion solar mass black holes when the universe was less than 1 billion years old. Explaining their rapid growth remains challenging. Can event horizons truly exist in exact form, or do quantum effects modify them? Does the Firewall Paradox have a resolution preserving the equivalence principle, or must we accept violations? What happens during the final moments of evaporation? Does anything remain? A Planck mass remnant, perhaps? Or does the black hole disappear entirely? What would this mean for the information it contained? These questions drive research, promising new insights into gravity, quantum mechanics, and the cosmos. Each potential answer opens further questions, perpetuating the cycle of discovery. Black holes reveal the interconnectedness of phenomena across vast scales, from quantum fluctuations near horizons to gravitational waves propagating across the universe, from microscopic physics to cosmic evolution. This interconnection reflects nature's underlying unity. Hawking radiation connects the smallest and largest scales. Quantum fluctuations at the Planck scale, 10 to the minus 35 meters, determine the evaporation rate of black holes billions of kilometers across. The physics of the infinitesimal affects the evolution of the gigantic. Black hole entropy connects thermodynamics, a macroscopic statistical theory, to quantum gravity through the horizon area. Counting microscopic states requires quantum gravity, yet the entropy affects macroscopic observables like temperature and evaporation rate. Micro and macro influence each other. Gravitational waves from black hole mergers connect events billions of light years away to detectors on Earth. Collisions involving objects containing millions of solar masses create spacetime ripples detected as displacements smaller than atomic nuclei. Cosmic violence creates infinitesimal effects, yet we measure them. Black holes in galactic centers connect to star formation throughout galaxies through feedback. The accretion disk around a black hole, mere light hours across, affects gas hundreds of thousands of light years away, regulating where stars form. The tiny influences the vast. Even more profoundly, if the holographic principle is correct, information about black hole interiors is encoded on their boundaries. The three-dimensional interior reduces to two-dimensional information on the horizon. Volume and surface, interior and boundary, are not independent but deeply connected. These interconnections suggest that nature cannot be understood piecemeal. Separating phenomena into isolated domains, quantum and classical, small and large, local and global, is approximation. Contemplating black holes from birth to evaporation provides profound perspective on existence, time, and our place in the cosmos. The scales involved spatial, temporal, energetic, dwarf human experience. yet we can grasp them through science and imagination. A stellar mass black hole contains perhaps 10 times the Sun's mass, compressed to 30 kilometers radius. The Sun contains 1 million Earths. Earth contains 7 billion humans and countless other living things. All of this, the entire history of a massive star, all the planets that might have orbited it, all the potential for life, collapses into a region smaller than many cities. Yet this is tiny compared to supermassive black holes containing billions of solar masses. Sagittarius A*, at the Milky Way's center, contains 4.2 million suns. If you could somehow hollow it out, you could fit Earth's orbit inside the event horizon. The black hole in M87 could contain dozens of solar systems. The timescales are even more humbling. A stellar mass black hole takes 10 to the 67th power years to evaporate, a time so long that writing it in years requires 67 digits. The universe is currently 13.8 billion years old, about 10 to the 10th power years. The black hole's lifetime exceeds the universe's age by a factor of 10 to the 57th power. Put another way, the current age of the universe is to a black hole's evaporation time as a single second is to 10,000 billion times the universe's current age. We, ephemeral creatures living decades in a universe billions of years old, can nevertheless understand black holes through mathematics and observation. Our minds, products of biological evolution on one planet, can grasp cosmic phenomena operating on scales of space and time beyond any practical experience. This is the triumph of human intellect and scientific method.